check, check, check. Do we have sound? Sound check, 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 check. Do you hear me? Live stream? Are you on yet?
No, I'm not on.
Let's see. How do I add particles? Okay, that's gonna work. Excellent. Oh, we are going chronologically. We've gone to the 80s.
Sound check sounds good. Sounds great. Dang it, I forgot my AirPods. Oh no.
Do you want a wire? Do you have a audio out? I can get you some wired ones.
Oh no, it's okay. Also, I don't need audio.
Somebody has to have audio. Do you have audio?
Yeah, actually, okay,
I'll get you some. I'll get you some wired ones.
Thank you.
Am I on Zoom here? They shouldn't come late because there is the makeup super quiz here. Join with meeting ID. Join with meeting ID. Join that one, please. Join. Oh, sorry. Oh, come on, don't give me trouble here. Good morning, everybody. Post-exam. You'll be excited, of course. Post-exam day, we do the midterm makeup question. So we take the question that was most missed on the exam last night and give you a chance in Chem Quiz style to retake that and get your point back. We'll do just a short recap and give a chance for everybody to join, so the latecomers have a chance. Of course, we shouldn't have pity on the latecomers. Melissa, how many do we have in the Zoom? 6 times 13, so not very many. 78. 87 on the live stream. So we're pretty close. So that's good. I'll do yeah, to get your credit, of course, you have to respond from a Zoom or from the Zoom. So dial up the Zoom, make sure you're there. Reminder for the 20th time, you get your attendance credit by responding at least once during the live stream from the Zoom. So all your technology has to be in play to get the credit. So last time before the exam, we were talking about the kinetic theory of gases. So we had these properties of gases that were they were very tiny compared to the volume of the space they were in. Negligible volume for an ideal gas. Point masses. They did collide with each other though. So the collisions were elastic, perfectly elastic, no energy lost, perfect momentum transfer. They collide with the Waals. They have an energy, and this was a result we actually were able to kind of derive somewhere. Not a formal derivation, but we saw the result, the famous and very cool result that the kinetic energy of a sample of ideal gas, number one, it's all kinetic energy. It's the motion of the particles, and two, completely independent of the particle or the size of the flask or pressure or anything. The energy dependent on the temperature only. And we could do that for the entire mole. We could do it per mole. You could put an N in there if you had more than one mole. And energy is an extensive property. It depends on the extent of the system. So if you have 2 moles of gas, you have twice the energy of a mole of gas contained within the motion of the particles. And we could do it per particle. Here's the average kinetic energy per particle. And that was related to the temperature, of course, as well. And this time you use the Boltzmann constant, this incredibly tiny number. And you can see it's about the opposite of the size of a mole, 10 to the minus 23rd. And that gives you the average kinetic energy of a particle, an individual particle in the sample. And we looked at those distributions of velocity. So clearly there's not one velocity. There's a distribution of velocities. They go by temperature and mass, you can predict the relative properties of the distribution. And that's a famous exam question. You look at one distribution and you're asked, how does it change if I change the temperature or the mass of the particle involved? And we saw if the red here is our base, our standard distribution, lots of various speeds, very few particles going zero or stopped, very few particles with very high kinetic energy, and the total number of particles under this, that's the actual quiz, got a preview there, actual number of particles. If you lower the temperature, that distribution squeezes down, you get a smaller overall distribution of speeds. So you don't have the same extremes of speed you did in the higher temperature. Or if you drop the mass, excuse me, in this case, if you increase the mass, you get a smaller distribution of speeds. And that jives exactly with our idea of the total energy. So if you have a higher mass, energy is, of course, the kinetic energy is, of course, 1/2 mv squared. That's the classic expression for kinetic energy. And that has to be the same regardless of the gas. So if you have a higher mass, you have to expect a lower average velocity. And we call that the root mean squared velocity. And we can plot that on the plot. That RMS has to go down. The overall curve amplitude has to go up because the number of particles under the curve stays the same. That's the total number of particles. And then we can identify straight away that the VRMS, that is the number of particles. You can read the number of particles off the plot. VRMS corresponds to the number of particles with exactly that average kinetic energy. So that's the number of particles that have the average kinetic energy. So they have the average speed as their speed. And you can see most of the particles, the majority of the particles have less, majority of the particles have less than that velocity. So we saw also that the curve does go to zero at zero velocity, zero speed, because of this v squared term. It favors lower energy because of this energy distribution term. This says e to the minus kinetic energy over kT, that lower energies will have a higher number of particles. This is e to the minus kinetic energy over kT. So lower speeds are favored. And we said that that jives with our understanding of nature as well, in that everything else being equal, particles would tend to go slower and favor and even stop if there's forces involved. If you, there's the quiz, we're gonna do it in a minute, so it doesn't matter. If you went to lower temperatures. However, that curve, overall curve, is forced to zero at zero because of that speed squared term. And that was interesting too. We said the speed squared appears for a similar reason that we use the amplitude squared in our wave functions. That is, there can't be a negative population. So we square everything to get this positive probabilities in our wave functions. Same things here, velocities can have plus and minus direction. So if we did take the overall average, it would be zero, because all the pluses would cancel all the minuses. So we square it, and then we take the square root of that squared. So we get back to a speed but we square it first to get that magnitude, then take the square root. And we called that the root mean squared speed. And that root mean squared speed varied with the temperature and the mass in a very predictable way. It goes as the square root of the temperature and 1 over the square root of the mass. So as promised, do we have a live stream population or a Zoom population of near 100 now?
As soon as you made that announcement, about 20 people joined.
I really hope those people have been paying attention and that your attendance, I mean, read the course information, and we've tried to say it, is correlated not just to responding, but responding while you have joined the Zoom. So we literally take the Zoom attendance every day, we correlate it with the iClicker, make sure the time was correct, you were in a lecture during the live stream, and that's how you're awarded your attendance credit. So the most missed question on the exam, complete surprise to me. You notice the exam wasn't very computational. You didn't have to get your calculator out very often. In fact, if you're clever, you didn't need your calculator more or less at all. Even the ideal gas questions, if you looked at them carefully, they were all just ratios. So you could have said, oh, the volume expands by a factor of 3. So the pressure goes down by a factor of 3. So you could have done even the ideal gas questions very quickly. We don't expect you to realize those things as freshmen your first time through, but as a learning experience, you can, especially with ideal gases, just use ratios of pressures and ratios of volumes and ratios of numbers of particles when things change, so that you don't have to do PV equals nRT 5 times to get a partial pressure or a total pressure. But we gave you plenty of time on the exam, so you could do that if you had to. So the most missed question, believe it or not, was from the first section on the exam, the multi-electron atoms. And the question was, which element can have the electronic configuration 1s2, 2s2, 2p6, 3s1? And the poll is started. So you'll have this locked on your screen for your iClicker. That means I can go to this and show you the periodic table. And again, you're in Zoom rooms, you can turn on your microphones and you can talk about this. So if you struggled with that question on the exam, even if you didn't, open up and talk. If you got it, if you nailed it, open up and explain it to your friends. This class is not curved. You're not competing with anybody. If everybody gets above 90%, in the end, everybody gets an A. So no competition in Chem 1. Talk to each other. Help your neighbor. Altruism, the theme of Chem 1. So no rush. We'll give you a full couple minutes, and I'll tell you before we close the poll. Okay, we're coming back. There's about 93, 94 of you. You've had about 3.5 minutes to think about this. So go ahead and push your button. We got 98 responses. 99, let's go ahead and we'll put Ryan's screen up here so we can see the distribution. And Ryan, let's not, okay. You're not showing the distribution yet, right? Okay, I want you to stop. Can you stop the voting first and then show? We don't want people changing after they see the distribution. So there's 101 of you. Countdown, 10 seconds, and we'll stop it. 9, 8, 7, 6, 5, 4, 3, 2, 1. We'll stop it and look at the distribution. And sodium and all of these equally popular. And this is, I guess, kind of the result that makes sense in a way. I'll tell you, this is almost exactly the distribution on the midterm. In a sense, that's good. The worst question on the exam was split half and half, and it was split half and half on a question that logically maybe could have been half and half. So that means the exam questions were good overall. There wasn't a question that stood out as being particularly difficult. Even this one, you got the distribution you expected to get. And I put expected in huge quotes because this was meant to be a giveaway. This was meant to be the easiest question on the exam. And maybe I didn't say it often enough, but if you take nothing else home from Chem 1A, take home the fact the only thing that identifies the nature of an element is what? The number of protons in the nucleus. Any element can have this electronic configuration, theoretically. For some, it would be rare because you'd have to take off or add a lot of electrons. But all of those elements could certainly have that electronic configuration. They would have a charge, but all we said was which element can have the electronic configuration, and all of those elements can have that electronic configuration. Some would carry a charge. They'd be an ion when they had that, but being an ion doesn't change the fact that you're argon, doesn't change your elemental status. So in a sense, I was disappointed because I said that so many times, but take that as a learning experience. You can bet that'll show up on the final. So half of you get your point back for this. And it'll be a course point, so we'll multiply by the appropriate multiplier. Okay, so we'll go back to our presentation on my end. And we'll continue with our discussion. So whip through these animations. So of course the answer here, all of these, and we'll just pick up where we left off. We have the root mean squared velocity, a function of only the temperature and the mass, and we take the root mean squared, we square it to get rid of the pluses and minuses, take the average, and then take the square root of that to get our average speed in the system. And we call it the root mean squared speed. And we did this chem quiz regarding that plot of RMS speed versus square root of temperature. And then we arrived at, we didn't derive this, we looked at the nature of the function, the distribution of speeds, and we did the obvious chem quiz then. We have the Maxwell-Boltzmann distributions, that's what they're called, at 300K for bromine and something else. So we know that if you go farther out, that that represents a lighter element or a higher temperature. In this case, they're both 300 K, so it has to be a lighter element. And we went out by a factor of 2 there, so we were able to tell from bromine to X, we had twice the mass, and we know the mass goes as 1 over the square root, or the RMS goes as 1 over the square root. So in order to get twice the velocity, we'd have to have a quarter of the mass, and we had a quarter of the mass at argon. And remember, this is Br2. So the mass of bromine, 160, a quarter of that, 40 for argon. Forgive me for my monotone. I'm still struggling with my voice, and I can't decide. I tried to not speak all weekend, to just be really quiet and see if that helps, but I'm still have this feeling that any minute my voice is gonna go away. So let's do this. Let's calculate one, and we're just gonna do a order of magnitude calculation. And we say this all the time in science: an order of magnitude is a power of 10. If you increase by a order of magnitude, you go up by a power of 10. So that's an order of magnitude step from 1 to 10, and from 10 to 100 is an order of magnitude. We want to know what's the order of magnitude of the RMS speed for bromine at 300 K, what we just looked at there. So what is that number? Go ahead and think about that. We'll start the poll. Okay, we're back. So the question is, if you if you have a bromine at around room temperature, how fast are they going? And you can do this calculation for the molar mass of bromine. I didn't tell you explicitly, and maybe I feel bad. This is low stakes, so this is a learning experience anyway, and here's part of the learning. You have to put the molar mass in kilograms. And you haven't really seen that before, but whenever you're doing any kind of calculation, always use the standard unit for mass, the standard unit for distance, the standard unit for temperature. And we do have standards. Everyone has agreed that if we're going to talk about mass, we're going to do it in kilograms, not grams. So when I define a joule has kilograms in it, not grams. It has meters in it, not feet or centimeters. So the standard unit for distance is a meter, standard unit for mass is a kilogram. So you need to put those in. Standard unit for time is seconds. So you can't do anything per minute or anything. This gives us meters per second, and it comes out, you can see just kind of roughly doing the math, that's going to be a factor of 100 for the RMS. Comes out to about 300 meters per second. So that, if we stop and talk about the magnitude, that is really fast. So the RMS velocity for bromine is 300. For a lighter particle, so bromine is very heavy. For a lighter particle like oxygen, we know the Maxwell distribution skews to faster speeds. So the oxygen particles in this room, which are just a fraction, a tenth of the bromines, a fifth of the bromines, are going 25 times faster. So that is a crazy amount of speed. The particles in the room right now are hitting you at thousands, from hundreds to thousands of meters per second. So those are the speeds of bullets, thousands of meters per second. These are the speeds of people running really fast. That's about my top speed, a meter per second. I finish just behind Usain Bolt in the 100 meter. So we can see this if we look at this demo. And I think I'm just going to try to touch that. Nope. I'll go back one. Again, we're using our new system here. So I should, that's a link. Nope, can't touch it there. I'll go over here and I will touch that. And we've already got it loaded, so I'll stop that loading and we'll go here. So here's Lonnie with that exact setup. He's going to put bromine in this Oh, the volume isn't coming from here.
First, they'll fill one end of the flask with gaseous bromine, open a valve, and let it race to the other end of the flask.
So he's going to put bromine in this flask. Bromine is a gas at room temperature. This very heavy element, you wouldn't expect it to be a gas. We'll decide why it is a gas in a few minutes. I might have paused it. So there's the brown bromine gas. Over here, we're going to see it race to that side, and that is just about 2 meters. So that should happen immediately. As soon as he opened the flask, a tenth of a second, the bromine was across that, to the other flask. So very rapidly across the flask. Now that other flask was evacuated. So the whole system was evacuated. So the bromine raced against nothing. And that's a very important point. The bromine was not sucked over to the other side of that flask. We've talked about this before. There is no such thing as suction. All there is pressure. So why did the bromine go flying over there? Well, it has particles moving in that direction at 300 meters per second. So if there's no particles to stop it from moving 300 meters per second, the particles that are going that way just go that way. The vacuum does nothing. Vacuums don't do anything. It's the bromine particles with their kinetic energy that go flying across there. If there had been air in there, then it would have diffused. It would have met resistance of other particles. And instead of its free velocity, we would have seen its diffusion velocity. And that diffusion is much slower. We can calculate by diffusion how long it takes a individual bromine to cross a football field. And that is on the order of hours because of all the particles it'll bump into along the way. So if I were to race the bromine would have to go slower than a meter per second for me to win. So we'd have to have that 2 orders of magnitude, factor of 100 in speed. And we know that factor of 100, how cool do we have to get it to go down by a factor of 100? We have to take the square root of that. So the temperature goes down by a factor of 10. So we'd have to get to 30 Kelvin for me to beat the bromines running across 100 yards. That's cold, as you know. Nitrogen, the air would be frozen at 30 Kelvin, giving me a slight advantage. Okay. I don't have to change sources. I'm in the right place. So let's go now and talk about these real effects of gases. So far, we've talked about ideal properties of gases only. What happens when it's real? Well, we've seen for ideal gases, the pressure times the volume is a constant. So if we take a pressure P1 here, we'll plot it at temperature T1. And I'll plot something like a real gas on this side and an ideal gas on this side. The real gas at low pressures, you can calculate its volume. And for the real gas at extremes, very low pressures or very high volumes or very high temperatures, it does behave ideally. That's why the ideal gas law helps. Even real gases behave ideally, even at standard temperature and pressure. So around 300 K in an atmosphere of pressure, there's quite a bit of ideal behavior in gases. Many gases. So if I compress this a little bit, so I drop the volume down and the pressure goes up. We know that. Same thing, I'll compress my ideal gas and my real gas. And again, the pressure goes up as the volume went down. So that we expect. I'll compress it again. And this is just going to keep going along this curve. P times V is a constant for our ideal gas. Something's going to happen eventually for the real gas. I will compress one more step for the ideal gas and the real gas. For the ideal gas, the number of particles never in the real system, eventually something's going to happen. And I think you know what that is. What happens is you compress the gas until you get a liquid forming. You go through a phase transition. So you can compress gases and cause them to turn into liquids, not just by reducing the temperature. You can put enough pressure on a gas to convert it to a liquid. If it converts to a liquid, some of the gas particles have left the system. They've left the building. They didn't leave they didn't leave the cylinder, but they left the phase. So they left the gas phase and entered the liquid phase. So there are fewer particles in here. So now N in the ideal gas law takes into account. You brought down the volume. You'd expect the pressure to go up, except the number of particles goes down due to that condensation, and the pressure does not change. So this phase change event, at that point, P times V is no longer a constant. Something happens here. We have a phase transition, a singularity in the PV curve. We can't define the slope at that point as or the change in slope at that point, the curvature at that point. So for the ideal gas, we continue to compress. The particles never liquefy. Here, we eventually get all the particles to liquefy, and then the pressure dramatically changes with volume because you're pressing against a liquid. And that's very hard to compress. You need huge changes in pressure to change the volume of a liquid. So that's real gas versus ideal gas behavior. We can see that in the various demos we have ready to go here. So this one. We can see Lonnie.
Gas condenses, the volume decreases by several orders of magnitude.
So what Lonnie's done here is he has steam, liquid water in those cans. And I'll pause that. So steam in the can. So we put a little bit of water in, put it on a hot plate. The can is filled with steam. That's gaseous water. Gaseous water, as we know, will not behave ideally throughout the entire temperature range or volume and pressure range. So when he rapidly cools it by going from the hot plate to the ice bath, the can is crushed. And why is the can crushed? Not because of suction or a vacuum. It's crushed because the pressure inside dramatically drops. We saw that in our curve. The pressure, the volume dramatically drops of the gas. That dramatic drop in the volume inside corresponds to a pressure drop. The pressure now of the outside air is much higher than the inside liquid water, and the can is compressed by the atmosphere. So he'll do it again. He'll take a can and invert it, crushed as the water condenses. And Lonnie also does that with a bigger can. So here's a giant can. He's done the same thing, heated it up and put it in an ice bath. So there's steam inside here. And let's see the steam condense in the ice bath. This giant sturdy can. What'll happen as the temperature drops? Temperature is going to drop more slowly. It's a bigger volume, less contact with the ice. And as it slows, we don't have the volume on. Even if we had the volume, I don't think you could hear it. But there's one crush to the can. And continues to cool. And even that large can is crushed by that that external pressure and low internal pressure. Tons of fun there. So let's go now to a different temperature. So if we go to a different temperature, this is another isotherm, and that was on the exam. Some of you would have seen that, and we talked about that. If I go to a higher temperature, what has to happen? Well, if I go to a higher temperature at constant pressure, so this is pressure, higher temperature at constant pressure, something's got to happen. Higher temperature at constant pressure, I have to go to a higher volume to keep the to obey the ideal gas law. So this higher volume means this isotherm at higher temperature is up the plot. So that's a higher temperature T2 and yet a higher temperature T3. These isotherms move out and up, but still obey the ideal gas law. What about the real gas? Well, they're not going to behave ideally. And you're going to find a point. Let's go very high temperatures, they're going to behave ideally. PV is a constant. As you drop the temperature, the first point at which you see this non-ideal behavior, the onset of real behavior, is what we call the critical temperature. It's the temperature where condensation initially starts. It's the point where you see this discontinuity in the slope of that line. It eventually becomes a sharp point, and you get the pressure flatlining. This is the critical temperature, the onset of the onset of real behavior. It's the separator between ideal and real behavior for real gases. Call that the critical temperature, the temperature at which phase changes, real behavior can begin to happen. Above the critical temperature, no phase change. You can compress the gas as much as you'd like. If you're above the critical temperature, you don't get a phase change. So we have this proper definition of critical temperature. Above the critical temperature, the gas behaves ideally. I don't get a liquid. The compressibility goes to infinity. The compressibility is the curvature of that line. Don't have to know that. The critical temperature, onset of real behavior, the divider between real and ideal behavior. So if the ideal gas law breaks down, what do we replace it with? So when we don't have ideal behavior, when we're below the critical temperature, is there a new ideal gas, excuse me, is there a new equation of state? Is there a new state equation for the pressure, volume, and temperature? And there are many. People have derived many expressions, and these are empirically derived. So by empirical, I mean you have to do experiments to arrive at these expressions. There are ways to do a somewhat theoretical approach, but for each gas is going to be different. So these constants have to be measured in, you have to do an experiment to get this exact expression, and it's going to be different for every gas. Every gas condenses, well, many gases, as you know, condense, and condense is the same as boil. That's the liquid gas phase transition. So they boil at different temperatures. So this term here adjusts for the collisions and attractions. You know, the collisions are going to go like the number of particles, more collisions, more volume, less collisions. So you have the a factor of the collisions in there, and this A factor times those collisions accounts for the attractive forces that actually cause that condensation. And if you overcome those attractive forces, causes the boiling. So we have this expression here, and these terms, we adjust the volume. We adjust the volume for the finite space the particles take up in the overall volume. So we reduce the overall volume available by a little bit because the particles take up some of the volume. And we change a factor of the pressure based on the attractive nature of the particles. No longer perfectly ideal collisions, but they average out to more or less ideal conditions. So the kinetic energy is preserved in a gas as long as the temperature remains constant. So you do have to provide some energy for a real gas to maintain gas phase, to maintain the kinetic energy at a given temperature. Gases would eventually slow down if they were in a, or the temperature would decrease. They would either condense if they were fixed, or they would spread out infinitely if they had infinite volume to deal with. So here are some of those numbers for various gases: helium, carbon dioxide, and water. So the A factors have something to do with the collisions and attractions, and collisions in general are about the same for all the particles. So collisions, frequency of collision doesn't change that much if the particle changes, but the attractive part does. And you can see some gases have a very high attractive component, water notably. And you can see that reflected in the boiling points. So higher boiling points, higher condensation temperature, higher boiling temperature for the gas because of these attractive forces. You have to put more energy in, go to higher temperature to overcome the attractive forces in a real gas like water and keep it a gas. And you can only keep it a gas at high temperatures. You have to get above the boiling temperature, which happens to be close to the critical temperature for water at an atmospheric pressure. So let's think about that. Which is true of this critical temperature we're talking about for ideal versus real gases. So we'll talk through this one. Well, if you're going to compare real and ideal gases, this critical temperature is a measure of the it's the dividing line between ideal behavior and real behavior. So I can say on my PV diagram that I'm going to have real behavior of the gas here at lower temperatures and more ideal behavior up here. And ideal meaning it does not condense, it does not become a liquid, it stays a gas. This condensation is what differentiates real and ideal behavior. And as we know, on our PV diagram, higher temperatures here, this T is greater than the critical temperature. And here below that, this temperature here is smaller than the critical temperature in this region. Okay, so which is true of an ideal gas? Well, an ideal gas doesn't have a critical temperature if it's perfectly ideal. So you can continue to cool. You can continue to cool your, your ideal gas as far as you'd like. And the ideal gas, PV is a constant above and below. The real gas we'll do in green, critical temperature, well, why don't we do it in yellow or orange? The real gas below the critical temperature starts to do that condensation. You get free contraction. That pressure drops, pressure doesn't change. So you can change the volume for free. There's no pressure pushing against you at that point because the pressure stays constant in the gas. So you can reduce the volume, you're pressing against particles, and then you get to the point where it's going to condense. You've got enough pressure in the system, it condenses, it starts condensing, and then the number of particles decrease, so you can press for free in that region because nothing pushing back against you, because every little bit you push, particles leave the system from gas to the liquid. It's a free compression in that direction, a free expansion in the other direction. So in this case, you know, the critical temperature for an ideal gas is always greater than that. Is always, I'm sorry, less than that of the ideal gas. Critical temperature greater than the ideal gas, because ideal gas, it doesn't have a critical temperature. 0 would be the critical temperature. Never displays real behavior. Pardon me. Take a quick drink here. Should have taken a break for that. Sure. So why does this happen? So now we know a lot about these gases. We know about their energies. We know how they behave with pressure and volume. We have to add this whole attractive force to the equation. And literally, we add it to the equation. So we take PV equals nRT, we add attraction to the equation. So if you're an ideal gas, there is no attraction. So here, what I'm doing here is I'm plotting the attraction between the particles versus the distance between the particles. And that never changes. It's always 0, no attractive forces for the ideal gas. And we know that energy and temperature are linear for an ideal gas and behave that way to a very great extent for real gases. So the average kinetic energy of the particles is given by the temperature, straight line, slope 3/2 kb. What about a real gas? Well, for a real gas, we get this famous potential curve that we've talked about many times, that as you come closer, attractive forces increase, and we can see those attractive forces increasing. The interaction energy, the amount of interaction between them, in this case, the attractive force, causes the system to go to lower energy with distance. And we know that if things attract each other, we say their energy drops as a plus approaches a minus. In this case, we could have uncharged particles or particles with dipole moments. We're talking about real particles here, so they could have actual charge contributions causing an attraction. Even nominally neutral things. And when I say nominal, I mean the average or the common condition. The nominal condition for atoms or many molecules is uncharged. But we'll see that there can be things are not static. Electrons aren't static. So you can have instantaneous little charge separations. So how does that work? I think we have a demo queued up for that. Easiest way to do it for me is go here and look at interactive potential. So here, there is that curve. And here are two particles in purple. If I take them far apart from each other, that interaction energy goes to 0. We defined that. Remember, the farthest apart is 0 energy. As they come together, we see an attractive interaction. And we know the shape of that plot. That was going as 1 over the distance, negative 1 over the distance, because of the Coulombic part, the plus minus attraction. And that goes to a minimum at a certain distance. There's a certain most stable distance where that energy of stabilization is ideal. If there was nothing else happening, if there were point charges, that would continue. This line would continue down. It doesn't in this case because the particles are real. They're going to start touching each other. And when they start touching each other, then the interaction becomes bad again. You're physically squeezing them into the same space. So the energy goes dramatically up after that. So two competing factors, the physical space that the particles are in, a Pauli exclusion, if you will, and the attractive force. I think we can show them. So you can see here, attractive and repulsive forces we can put on. So the attractive forces, they've categorized them as van der Waal forces. That real gas equation was van der Waal equation of state. So those attractive forces we can put on, and they're going to appear as these orange vectors at large distances. The attractive forces are 0. They're too far apart. They increase as 1 over r squared. So the potential goes as 1 over r. Don't worry about that distinction. We've seen this 1 over r interaction energy. And as they go close, look what happens. Those attractive forces get very large. The potential is getting quite small. But something else is happening. This purple vector is coming in. That's pushing them apart because we have repulsive interactions between the electrons. The electrons are all negatively charged. So the negatively charged electrons and the fact that I'm squeezing everything into the same space, I get a Pauli principle. Particles can't, fermions can't occupy the same space. So as I continue to come close, I find a place where there's equilibrium, harmony between the repulsive force and the attractive force. All my arrows are the same size. If I go closer, I drag my particles closer, then that big purple repulsive force dominates, and they are, that interaction becomes unfavorable. That's totally fun. And you can do that. They have some real actual gases. You can do it for neon or for argon. And then these potentials, these attractive forces are calculated from the van der Waals equation. So they put those constants in for the attraction. Repulsion stays similar, but bigger things, of course, start interacting earlier. So that's totally fun. Play with that one. That'll be in Prism in your graphics windows when Melissa does her amazing uploads. So when does this stuff matter? So this interaction energy, when it's at its greatest effect, the attraction has the greatest effect at lowering those energies, at trapping the particles in that well. The particles want to stay here. And if they have motion, they're going to bounce in and out of there. They'll hit this wall and go, whoops, bounce back. If you lower their motion, lower their energy, they're going to get trapped in that more stable, lower energy condition. And you can, I'm sure, be correlating that. Some energies at some temperatures, this interaction energy will be overcome by the kinetic energy. And that's what I've plotted here. I've taken this energy difference, that interaction energy, moved it over and plotted that magnitude on the energy axis of my energy plot. Where that interacts is the critical temperature. So above the critical temperature, I can overcome that interaction energy. Below the critical temperature, I have the attractive forces start to win. They're bigger. And that makes sense. If the attractive forces become of the same order of magnitude and then larger than the average kinetic energies, some particles, the very slow moving ones, this is an average, remember, the very slow moving ones, that attraction interaction will be much bigger than their kinetic energies. And those are going to stay in that potential well. They're going to stay down there. And that is going to be a condensation. Let's plot that in terms of our Maxwell-Boltzmann distributions. So here's a Maxwell-Boltzmann distribution at the critical temperature. So the average VRMS root mean squared velocity represents the number of particles with the average velocity. So here are, right here, the number of particles that actually have that velocity. I think I put that on the plot. Yeah, so those are the number of particles that actually have that velocity. So you could calculate their average kinetic energy from their kinetic energy with the mass in kilograms. So you'd get an energy of interaction there in joules, and you can see the units for joules in here. If this is indeed an energy, then that better be in joules. And if that has to be in joules, the units of joules have to be the mass unit, kilograms, and the velocity squared unit, meters squared per second squared. So a joule is a kilogram meter per second, kilogram meter squared per second squared. And that's why you need to use kilograms when you're talking about energies and VRMSs, and you use joules, or if you use the Boltzmann constant. If you got to multiply something by the Boltzmann constant or the gas constant, your masses better be in kilograms and your velocities in meters per second. So we can see now all these particles are the particles that have lower kinetic energies than, oh, poo. Let's leave that up there. All these particles, just move this thing. are the particles that have less than, on average, this average kinetic energy. They have, on average, less than this interaction energy, KB times T. I put in KB times T just with this squiggle, within 1.5 of the KB times T. So that interaction energy, you have lots of particles with less energy than that. These particles have the potential to condense. If I look at temperatures less than the critical temperature, I have more particles. This energy, this point I have to keep the same because that's my energy of condensation. That's my benchmark there. When I change the temperature of the system, more particles now have below that benchmark energy. And you know what's happening? These guys here with the very low energies, these particles here, they are condensing. And as those guys condense, what happens to the overall energy of the system? Well, the overall energy of the system has to drop. Particles are leaving the system. Albeit the ones with low kinetic energy, they're still leaving the system. That's reducing the overall energy. And this temperature will continue to decrease because of that. And you'll get that spontaneous contraction, that free contraction as you as those particles leave the system below the critical temperature. That is gorgeous. You have to admit that summarizes the universe essentially there. How all the particles in the universe are interacting with each other. Just soak that in for a second. I forget what the demo is for this. It's something. Let's look. Oh, it's that attraction energy again. So here's a little bit of a summary then in pictures. I've got the ideal gases here, the real gases here. Ideal gases, high temperature, you have a high average kinetic energy. So this is the average kinetic energy written out here, not the energy of an individual particle, or all, but some particles do have a velocity or a speed consistent with the average energy. Real particles, same thing. But real particles have an attractive component. The ideal particles do not. So as you go to low temperatures, lower kinetic energies, ideal gases don't care because they'll just go on average slower, have an overall slower kinetic energy. Real gases, though, that interaction energy becomes of the same order of magnitude, within a factor of 10, of the interaction energy, and those guys have the potential to stay in that equilibrium distance. They stay at that equilibrium distance, and you can kind of bet that's got to be related to the distance they are in the liquid. It almost gives you chills. The beauty. It is funny. Beautiful is just a crazy word. When you use beautiful in science and mathematics, it's when, everything makes sense. It all comes together in a beautiful way. Now, for many of you out there, that isn't coming together in a beautiful way today, right now, maybe the first time you've seen that, but go through that last slide if you can It's, I think, one of the most important slides of the class. Melissa will put a big star next to it somehow. Do we have a way to put stars next to things? I don't think we actually do. Let's think of a way to make that happen. I can't off the top of my head in any of the software.
I'll post it 5 times consecutively.
Okay, Melissa says she'll post it 5 times consecutively. This slide will be a factor of 5 more likely to show up. That's not exactly true mathematically, but more likely to show up in your Prism system when you're looking at the slides and you're correlating them to the video and text elements from the class. Oh, goodness. So let's talk through a chem quiz here. I'll go back one. I'm just going to talk through this one, Ryan. Which of the gases have the largest attraction energy, the largest delta U? And by mean largest, I mean most negative, the biggest in magnitude attractive force. And if you look at these 3, and in this case, you would think back to our van der Waals interaction and say, which of those, helium, carbon dioxide, or water, have the least ideal behavior, the most attractive force? And we said that this term, A, correlates with the attractive force. The largest one is for water. And we'll find out why that is. There they are in bigger print. The biggest attractive forces are for water. They will behave the least ideally. They'll have the highest boiling temperature, the highest temperature of condensation, the highest critical temperature of those, and water is what you're talking about there. Lovely chem quiz. So what are these intermolecular forces? They come in several flavors. Oh, shoot. I was messing around with the animations this morning, and poopy. The presentation we're actually looking at, I fixed the animations in a different version. Darn it. Okay, the animations are going to be messed up here, but bear with me. We might have to go through all the animations and just look at the complete slide. What starts first? Okay, a possible interaction starts first. So a possible intermolecular interaction, an intermolecular force, one source of that could be, as we said, if you have some plus or minus attraction, or some plus or minus fixed parts of your molecule. If you have a dipole moment, then yes, you have a positive end and a negative end of the molecule. And those, when they're aligned correctly, are an attractive force. So dipole-dipole interactions are one attractive force you can have in intermolecular interactions. What about those uncharged things? We said even the uncharged things attract each other. Something that overcomes the Pauli exclusion, that the negative interaction of electrons. What overcomes that? Well, we call those dispersion forces, and sometimes they're called London forces. As you know, I hate to use people's names. You probably noticed I've never said Boyle's law or Charles' law here in or have tried not to say it for ideal gases. I just want you to know the overall science. I don't care if you know who discovered it. Who discovered it is incredibly important. These people are giants in the field. Absolutely go read some historical accounts. It's beautiful. You'll really enjoy it. But we're just going to call these transient or induced or dispersion forces. They're transient, that is, they don't last very long. They're induced by random fluctuations of the electron cloud and what those random fluctuations can do to a nearby particle. So here's the two particles, and what I've shown here is the electron cloud transiently dispersed there. More negative here, the nucleus is there, more positive. So that interaction there, shifting back and forth, this causes this particle to have a transient, instantaneous dipole moment, if you will, a negative and a positive end of the symmetric, nominally symmetric atom. And that would induce, that negative charge could induce a positive charge, repel the electrons and in a neighboring particle. And that repulsion in the neighboring particle in turn would cause a transient attraction between them. So that's very low energy. I've plotted them in energy here. That's the lowest energy interaction, dipole-dipole. Higher than that because the charges are permanent. They're partial charges. They're not full, but they're there. And then there's perhaps the most famous, and for many of you who are MCB majors interested in molecular and cell biology and biological chemistry. And I will tell you, just because it's true, and I'm a chemist, I'm actually a biophysical chemist. I study the structures of biological molecules. This is one of the most important forces in those biological molecules, and it's one of the most important influential features in nature, hydrogen bonding. And we give it that term bonding, and we should definitely put the bonding in quotes. I'll air quote it. It's not a physical bond between molecules, but it's so strong compared to these intermolecular forces that it behaves like a bond, and in fact, it orders the system. It limits the degrees of freedom of the particles because it's so strong. And that happens when you have, one, a permanent dipole moment, and a hydrogen that can be attracted to a very electronegative element. This interaction, hydrogen being attracted to a negative electronegative element in another system or a negatively charged center. So this could be permanently charged because it's, we'll learn later, maybe that's an acidic species and there is a real full positive negative charge there, attracted to the positive, partially positive end of a water molecule. That interaction is much higher energy than any of these, on the order of 10 kilojoules per mole. That's why I put this little break in the internal energy or the overall energy curve, because this is much higher than those. And this really is near bond strength. Bonds are hundreds of kilojoules per mole. So we're within an order of magnitude of real chemical bonds when we're talking about this hydrogen bonding interaction. It's an intermolecular force. So let's plot some boiling points. Let's look at the effect of the masses and intermolecular forces on boiling points. So here I've plotted methane, silicon hydride, germanium hydride, and tin hydride, and I've pointed them, I've gone across the periodic table, I've gone down a column of the periodic table. So I've gone more massive And as you see, as I go more massive, I have a change in the boiling point. So I expect some larger intermolecular forces here, some lesser intermolecular forces there. Same thing for the halogens. Hydrogen chloride boils or condenses at a lower temperature, hydrogen bromide, hydrogen iodide. So you're expecting the higher boiling temperatures to correspond to greater intermolecular interactions. Here I've plotted sulfur, selenium, and tellurium dihydride. So another dihydride, sulfur. We can go one more over on the periodic table to oxygen, or one more up on the periodic table for oxygen, and get water. And look at the difference here. This guy has a dominant force is its dominant intermolecular force is the hydrogen bonding. Water is the classic example of strong hydrogen bonding. And look at what it does to the boiling point of water. Very high. You have to go to very high temperatures to pull these things apart. Here, what's happening is these things are just getting kind of bigger and floppier. So as they get bigger and floppier, you get stronger transient induced things. And that's kind of a modest effect on the boiling points. In general, bigger things, bigger atoms and molecules, the electrons are less firmly held and they have higher transient intermolecular forces. And you can see that in these trends. These guys in general don't have permanent dipole moments. Well, these guys have permanent dipole moments. So you have permanent dipole moments. You have dipole and transient dispersion forces here. And that's reflective, of course, of that increasing, but it's small. Those effects are small compared to when hydrogen bonding really takes off, when it's really effective. So HF, hydrogen bonding, and H2O, hydrogen bonding, causing that dramatic change in boiling point. Again, essentially a summary of everything you need to know about intermolecular forces. We're not going to harp on this in the class. We're going to just tell you there's 3 overall categories of intermolecular forces. We're going to say this one common among uncharged, nominally uncharged things. The bigger they are, the larger that transient force. That's reflected here. Dipole-dipole interactions, bigger interaction and common necessitated, you necessarily have to have a permanent dipole moment, and you have that here. That gives you this step, this big step in boiling points. These have, you can see these are all tetrahedral. They don't have dipole moments. You go up here, you have a dipole moment, so you have an increase in boiling points there. Dipole moments get stronger here, increased dipole moments here, and some hydrogen bonding, limited. When you get to the strong hydrogen bonding situations where you have a big dipole moment, permanent dipole moment, and available hydrogens, you get this giant change in boiling point. So there it is. Summarized everything you need to know about intermolecular interactions in one big chunk. So let's do a chem quiz. Which has the highest boiling point or condensation point? Remember, boiling and condensation are the same point in temperature. One is just going to the gas. One refers to going to the liquid, but the going is an equilibrium at the boiling point. Some are coming, some are going. So boiling and condensation at the boiling point are in equilibrium. Just as many boiling as there are condensing. Which of those has the highest boiling point? Let's talk about that for a minute amongst yourselves and see if you can come up with a common answer. Okay, I'll come back. I'll address it right now. And sorry, we're back and we're chatting. There's some complaints about the midterm makeup question. But first, let's look at this question. Ryan, let's see what people are thinking. Whatever you want to do, I don't care. So most of us are thinking water, and I agree with you. This actually, I think all of these may have been on that plot. So you could have just looked at the plot. You could have also said which has the highest intermolecular interactions, largest energies, and of course that is water. So that gives you the highest intermolecular interaction. So largest permanent dipole. So I've drawn part of the molecule. Here's the OH in the molecule. That's the largest dipole. So the molecule next door has the largest hydrogen bond, and hydrogen bonding always is the biggest influence. Okay, there's some discord over that question on the midterm. The one that we just did the makeup, people are saying that sodium should be an allowed answer. That one didn't say circle all that apply or any of that kind of stuff. There's one right answer to that question. The one right answer is all of these. The complaints coming in, I guess I can show it to you again. I can zoom back to that question. Here's that question. And I should tell you, if I say, if you take nothing else home from Chem 1A, take home the fact that the only thing that determines the identity of an element are the number of protons in the nucleus, you better take that home. And if our sodium is neutral, if chlorine has a negative charge, is it not chlorine anymore? No, that's the point of this. Every single one of these can have that configuration. if you talked yourself out of that because this is the neutral atom with that configuration, that's not what I said. I didn't say which neutral atom has that electron configuration. I said which element can have that electron configuration, not which one does or which one is negative or which one is positive. All of these can have that electronic configuration. Some would be an ion when that happened, but when you're an ion, that doesn't change you from being chlorine to being neon. All of these can have that electronic configuration. And I see what you're saying, but I specifically said this twice in the class. When we got to electron configurations, I said any particle electron configurations do not uniquely define an atom or an element. And I said when we were talking about beginning the first day of the class, the number of protons in the nucleus is the only thing that determines the identity of the element. Doesn't matter how many electrons you have. And even if you were saying, oh, that's nitrogen, those two facts should have rung home. I've been in lecture and Mark has been saying over and over again, electron configurations do not matter for the identity of the element. So if you had that argument in your mind, should have been outweighed by this word can and the fact that this is a better answer and the fact that I was harping on it a couple times in the lectures. So we've gone over, it's Tuesday, right? It's Tuesday though. So when it's Tuesday, I stay and answer questions. So office hours time. So are there things coming in the Zoom or in the live stream chat that we should? Oh crap! Oh, I'm getting to low battery. Do you still have audio? Still hear me? Okay, my battery's dying on the mic. Go ahead if there are any questions. Day after the midterm, everybody's tired. Not surprising that there aren't a lot of questions. That discussion we had today, I hope you all followed it. It's one of those discussions that you do have to let it sink in and go over it before you start getting questions. It's often the case too. So nothing coming in, guys? Live stream?
Possibly go over the kinetic versus interaction energy slide again. I think it was a very important slide.
Yes. So the question is, hopefully I don't run out of battery on my mic completely. But yeah, let's go over that slide. Now everybody's listening to me if I say something's important. Oh, now you're paying attention if I say something's important. What do I have to do to get you to listen? I feel like a parent. Well, there it is. So, why is this beautiful and why is this important? These issues right here, the fact that this appears twice in this slide, the average kinetic energy, I can plot that and it's a beautiful result. It's linear. Average kinetic energy is linear with the temperature of the particles or molar energy. And this is a classic interaction in chemistry and physics. We've looked at it many times, the interaction energy versus distance. We haven't talked about this part as much, the part where it gets very unfavorable when you're actually pushing things on top of each other. But we've talked about that interaction energy many times. As you get closer, things tend to have attraction energies go up. Now we know there's an optimum because if we get too close, the interaction energies go down until the actual physical dimensions of the particles, you're starting overlapping particles, and then they get unfavorable very, very fast. So you have an unfavorable interaction. You have an unfavorable interaction. Here, this is unfavorable. It's the overlap in space. So this is where Pauli exclusion starts to come into effect, or the minus interactions of the electrons. Physically trying to put things on top of each other in space is bad, and it's very bad, and it goes up very fast at low distances. And you have that competing with the 1/r that we've seen many times for the interaction energy. And the sum of those things gives you this very classic plot of interaction energy as a function of distance. So you have that beautiful result, and you can literally, this is a little hand wavy, but you can map that amount of energy, the energy of trapping the particle at that lowest point. You can find that energy on your energy versus temperature and correlate it with the temperature. That's a beautiful thing. Wow. And that is the critical temperature. You would think that's an important temperature. When is that energy have an effect on the system? Well, it has an effect on the system. First of all, what energies of the kinetic energies of the particles, this is an interaction energy that I'm translating into a kinetic energy. So this step is a translation from potential to kinetic energy. This is potential energy, and I'm translating it to a kinetic energy. And when I do that, I say, there's always an exchange between potential and kinetic energies. And when kinetic energies are bigger than potential energies, the kinetic energies win and things move. When the potential energies win, things are drawn together and slow down and stop. And here's the differentiating point. At temperatures, energies above the interaction energy, you behave ideally. You don't condense. Your velocities and your kinetic energies are bigger than the interaction energy that's trying to hold you together. And then we plotted that, and we looked at the numbers of particles that have those various energies. So then we go to it from the potential energy to the kinetic energy to the distribution of energies. I feel like a third grader running out of space at the end here. I think I can do that and erase this. There's a setting on the board that I can erase with my palm to turn that on so that I can just slap my palm up there and erase. I will start smaller here. So now you can look at, well, how many particles actually have kinetic energies above and below that interaction energy. And you can correlate that to your idea of, particles slow down and have lower kinetic energies. More have these lower speeds and lower kinetic energies at lower temperatures. So all of our understanding so far of the universe and particles are here. there's their attraction energies, there's their kinetic energies, and there's the distribution of energies. And this is so important because everything is statistics in the end. All these things are dominated by this statistical distribution of speeds in nature. If there weren't this large number of particles in this distribution of speeds, then these the phase changes would we couldn't understand them. They things would essentially never change phases. If you didn't have many particles with bigger energies, higher speeds, then nothing would condense. If you didn't have anything, a distribution with lower speeds and lower energies, then nothing would ever, I said that backwards. If you had a distribution of only low energies, then nothing would go to the gas phase. If you had distributions with so many higher energies, nothing would ever condense. So there it is, the universe in a nutshell. We're going to start talking. In fact, the rest of the class is basically these energies, kinetic energies, and then there's the very cool non-energetic, the purely statistical arguments of this argument, and that's the entropic effect, and that is really cool. We'll talk about that in a week or so.
James asks regarding the potential energy distance graph. So if you go past the minimum, you are experiencing U from when the two molecules are touching.
James is asking if you go past U on the kinetic energy, you go past what?
I think on the potential energy, you go past the minimum. Are you still experiencing potential energies from when the two molecules are touching?
Yeah. So the question is, if you go to shorter distances, do you still have attractive forces? I guess the forces are battling each other. So that's a very important plot, and we saw it here. And we have to go to a custom interaction so I can make the interaction strength big. So, and let's put those vectors back on. Oh, cool. Here's the animation. Let's pause that for a second. So if I take these particles far apart, as I bring them together, the orange vector gets very big, and that's the total attractive forces. And those are balanced at this minimum point. That is the amount of bad energy you get from coming close is balanced by the amount of good energy you get from being close. And as you get closer, then bad energy dominates. See that gigantic purple vector? As you get farther away, you get to that point where the attractive forces can win, and then going very far away, there are no forces. And that animation was fun because what it is showing you is the actual approach. And if you have lots of kinetic energy, does the attractive energy win? So here the particles are moving with respect to each other. We've got one fixed, but they come in and they bounce. But if they have lots of kinetic energy, they bounce back out of that well to a big distance again. This kinetic energy has to be low enough to trap them. And I can make that interaction energy stronger. Let's see if I can trap those molecules by saying, Well, now you have that much interaction energy. Ooh, look at that. I'm going to trap that guy near the equilibrium distance. So very strong interaction. And now its kinetic energy is about equal to the potential energy. And I have them bouncing here. I can make them go closer. And I've actually physically trapped them in that. I'm changing the atomic diameter, I think. Yeah. Trying to get the particle to move again. Oops, I can't get the particle to move. Maybe I just have to restart the whole thing. Oh, there's a reset button. And now let the animation play. How did I get it to play? It was fun. Move them. Oh, there. I just have to move them and they start playing. Okay, I got it. Custom interaction. Make the interaction strong. And move them. I see. Give them some kinetic energy. Drag it. I dragged it apart. There you have some kinetic energy. And now your kinetic energy virtually traps them. And I can increase the interaction strength and get that so they are very well trapped in that hole, very close to the equilibrium distance. They're not going far away and very close now. Oh, and look at that. It is, I think, oh, look at that. The interaction energy is sapping the kinetic energy, I think. Is it starting to get lower up that curve? Is that my imagination? Might be my imagination. Make the interaction a little stronger. Ooh, there. I trapped it right down there. I can't stop motion, but I really trap them as I make that interaction energy very strong. I trap the particles with that kinetic energy in that equilibrium distance, and that is going to be the condensation distance, the distance when they become a liquid. That's a lot of fun. Play with that animation and see if you can get some understanding. I think you can can you unpin? Pinned. Oh, I can just change which one is pinned. Can I unpin? Oh, I see. That's the pinned. I can't unpin and have them both move. Okay. Other questions? I'm just starting to play with it.
This is a long one, but if we use atomic potential energy as an analogy to help us understand these graphs, then can we say that kinetic energy at critical temperature is to the energy of molecule-molecule attraction as ionization energy is to nucleus-electron attraction?
Yes. Long but brilliant. Yes. The question is this analogous to the ionization energy? And absolutely, ionization energy, you're pulling those guys apart. And as they come together, when is the condition where that interaction energy is bigger than the ionization energy and it holds them together? And remember, we did that exact chem quiz. We said, as electrons come together, we had a bunch of ions, and we said, for which is that interaction distance the largest? And we said that interaction distance was the largest for the thing with the lowest ionization energy. So absolutely, when this thing is for all, this general thing is for all particles, electron nucleus, and that's why I said we've talked about this many times. It's one of the most fundamental things in science, nature, and chemistry. Yes, brilliant question. You've realized That is what's happening with particles as they come in contact with each other.
Can you please reiterate what is happening when you increase interaction?
The question is, can we reiterate what's happening when I make that well deeper? So and you guys can play with this. It'll be on the force. So first, let's go to a relatively low interaction energy. Oh, that's the diameter. A relatively low interaction energy. And start the particle moving. So here I have a relatively low interaction energy. If I make that bigger, and let me show, what happens if I show the total force? So here I showed in green the total force. Let's pause the animation so I can do it myself. As they come together, the attractive force is winning. You can see the attractive force is getting more and more favorable. That is, I'm going down in that well, and I get to the point where boop, the attractive and repulsive forces are equal. If I bring them closer together, now repulsive forces are winning. If I increase this interaction strength, I'm increasing those intermolecular forces. You could say I'm increasing the van der Waals. I'm increasing hydrogen bonding strength. I'm going to a molecule that has a high hydrogen bonding strength, or a molecule that has a permanent dipole moment versus one that doesn't have a permanent dipole moment. And that interaction energy is getting deeper, and it's easier. It's a deeper hole. That's literally a well. It's a deeper hole that the particle can get trapped in. And that deeper hole is stronger interaction energies. Does that kind of explain what's going on there a little better? Sweet. Well, it says we're getting indication from the student instructors that the questions are petering out. So great, guys. Go forth and learn this kind of stuff. And we'll talk to you tomorrow.